Dear colleagues, your attention is invited to a research paper on the topic, the influence of the degree of deformation on the grain size and the boundaries between them in metal alloys during cold rolling of sheets. The work was carried out by scientific and pedagogical workers of the Department of Ferrous Metallurgy and Foundry Production of Kryvyi Rih National University. In the modern world, the requirements for the quality and performance of metal products are constantly increasing, which completely depends on the internal structure of these parts, which consist of grains of different sizes. Therefore, the study of changes in the structure of metals and alloys under the influence of external factors during cold rolling is an actual task. The solution of this problem will make it possible to control the strength of steel during its processing and improve the quality of the resulting metal products. Deformation scheme. When metals are rolled, the plastic deformation of the raw material takes place, causing a change in its shape and size. This figure shows the deformation scheme, where you can see that ABB stroke A stroke is the deformation zone. In the top view, the deformation zone is shaded. Cold rolling produces strengthening, grinding and elongation of ferrite grains along the rolling direction. The total compression during cold rolling determines the final texture of the deformed material. A high degree of cold deformation produces fine grains. Ability to plastic deformation of metals and alloys is determined by the yield strength of the material, which also depends on its internal structure. We therefore investigated regularities of the influence of the amount of reduction during cold rolling on grain size and grain boundaries. This will allow adjusting the strength and ductility of products by controlling the value of compression during cold rolling of steel. Changing microstructure of steel. The microstructure of cast low-carbon steel has been studied and compared with the structure after cold rolling. Slide 3 shows the change in the shape and size of the grains during compression. The geometric characteristics of the metal structure were determined. That is the area of the intergranular surface and its volume, as well as the volume fraction of the surface of the volume of the metal. Derivation of formula for determination of grain size and metal after rolling. Here are the formulas by which the geometric characteristics of the structural elements of the metal were determined. The volume of the intergranular surface VMG was calculated by formula 1. According to the Hall-Petch law, the yield strength sigma T is determined by formula 2. The yield strength of metal during cold rolling is calculated by formula 3. Equating formulas 2 and 3, after appropriate transformations, the reduction value epsilon was determined, which provides a given grain size during cold rolling, according to formula 4. After performing mathematical transformations, we obtain formula 5 For the dependence of the grain size d in the metal after rolling on the reduction value epsilon, the proposed dependence will make it possible to control the change in grain size by the degree of reduction, which determines the prospects for controlling the strength of steel products. Parameters of internal structure and properties of steel at different compression values are presented in the table on slide 5. The table shows that with an increase in the degree of compression, the fraction of the intergranular volume, taken as amorphous, increases the yield strength of the metal and its hardening. Plots of the dependence of the fraction, percent, amorphous volume, hardening and shrinkage, depending on the grain size. A visual representation of changes in the volume fraction of amorphous material, the magnitude of shrinkage and the magnitude of hardening of the metal, depending on the grain size of the internal structure of steel, is shown on slide 6. The resulting graphs show that during cold rolling, the internal properties of the treated sheets, that is their grain size and the boundaries between them, the yield strength of the metal and its changes, can be controlled by adjusting the magnitude of the crimping. The effect of the degree of compression on grain size. Studies of changes in grain size as a function of the degree of crimping are shown in the graph on slide 7. Studies have shown that a total reduction of more than 80% in cold rolling produces sheets with an internal structure that has a minimum normal grain size and is characterized by maximum intergranular boundaries. It should be noted that the grain size decreases with increasing degree of reduction by hyperbolic function of the order n. The effect of the magnitude of compression, percent, on the hardening of the metal alloy and the proportion of intergranular volume, is shown in the graph on slide 8, which shows that these values increase almost equally with increasing strain rate. The results suggest that there is a correlation between the increase in yield strength of the metal alloy and the size of the intergrain boundaries, that is amorphous layer, which contributes to the strength of the metal. Conclusions. The changes which occur in the internal structure of metal products during forming have been analyzed, making it possible to establish dependence between the grain size of the metal alloy and the boundaries between them and the value of compression during cold rolling. The regularities of the effect of the magnitude of compression on the size of metal alloy grains, the boundaries between them and the hardening of the metal are established. It is shown that the grain size decreases with increasing degree of deformation by hyperbolic function of order n, and the proportion of intergranular amorphous volume and hardening of the metal increases by linear functions, which allows to control the strength of steel products by controlling the size of grains and their intergranular surface. That is by changing the value of compression. End of speech. The performance is over. Thank you for your attention.